Hello, this is Dan Alford with ARC Specialties. We're going to do a series on designing for automation. I've been doing this since the early 80s. We've learned a lot of lessons along the way and I thought I would share them with you. We're going to start off with RockBits. This is a rolling cone rock bit which was designed by Howard Hughes in the early 1900s and it's still in use today. I'm going to start with this example because I've been involved in the industry for 40 years and we've automated many of the processes. And while we were doing so, we observed a lot of things that needed to be changed, and some of them were and some of them weren't. So I'm going to go through all three of these scenarios with you. So the first process we decided to automate in this industry was the placement of the cobalt bearing alloy inlay on the bearings. It's on this, the journal bearing, the thrust face, the pin OD, and the pin end. Traditionally, this had been done with oxy-acetylene and a solid rod made out of what's referred to as stellite 190, which is a high carbon version of stellite 1. So this is a manual operation where they're welding this on or actually brazing it on with an oxy-acetylene torch. Simply not a candidate for automation unless you change the rules. So the only way we could automate this was to go to some process which is compatible with robots. So the first step was getting people to agree to a new welding process. The first guys that were automating this actually used gas tungsten arc or TIG welding and a cast rod. And that was a step up from the manual process, but it wasn't the final solution. The best solution was plasma, because the problem with cast rod feeds is the filler material and the direction of travel. You can only travel in the direction of the filler rod. With plasma, all of a sudden, we're using a plasma torch. We can move in any direction. We can control our heat input much better. And so once we got the industry to accept the fact that they had to go away from oxy-acetylene welding to plasma, that was the first step. Then we had to introduce robots into this process because we had to go from manual to automation. This is a great robot job. So that's how we succeeded in doing all of these surfaces on a rock bit, the journal, thrust face, pin OD, and pin in. And you can see the silver inlays here are actually the cobalt alloys. So, like I said, the first step was changing the paradigm on what welding process. Initially, people thought that we'd have too much dilution with plasma, but once again, the benefits outweighed the problems, and now the industry has pretty much switched over completely to plasma welding. But it goes on from there. For example, with plasma welding, and any other inert gas process, you really don't have any way to reduce oxides. So if you have any oxides in the system, they melt at a much higher melting point than the base material or the filler material. And so one way around that with plasma welding is you can actually introduce hydrogen gas into the shielding gas and it becomes a deoxidizer. Of course, there's a lot of inertia in the industry. Nobody likes hydrogen, it's flammable, it's explosive, it's considered to be dangerous. So actually the first machine that we built to do journal bearings, they refused to allow me to put hydrogen in as a shielding gas. And the irony is we built a second machine for another company, and the first company came in and observed the second machine running at a lower current, better weld quality and higher speed. And they said, how was that? And I said, well, they listened. They allowed me to use hydrogen. So they said, well, put hydrogen on all our machines. So now that's pretty much the standard in the industry. We're running 5% hydrogen in the shielding gas. So once again, it's a safety issue, but everything has risk and reward. In this case, hydrogen more than outweighed any safety risk, and we've proven that with no accidents over the last 30 years. So sometimes you have to change a rule. While I was working on one of these machines in Russia, I made the comment that since we're starting off with a rough forging like this is a pattern, we could change the geometry of this bearing while we were welding it. And on all the American rock bits, they leave a very thin edge right here. And we're supposed to weld right next to it and not melt it. Well, that's problematic, it's challenging. Wouldn't it be better if we extended this? So, you know, when I talk to the American companies, they say, that's going to require committee and much study and deliberation. When I was working in Russia, they said the parts will be ready in the morning. And so the fact that they listened to my suggestions made their welding process much, much easier by simply extending the end of the rock bit bearing by 1/4 of an inch. During the rough machining operation, it greatly simplified the programming of the robot, increased their acceptance rate on their machine, all at no cost, because we're going to machine this off later anyway. So that's everything I had to do with on the journal bearing, but then there's other areas to weld also on the rock bit. This area here is called the shirt tail. This is the ground engaging surface of the rock bit. So as you're drilling through the oil formations, this rubs against the rock. And if it rubs and wears, it'll expose the seal, the grease will leak out, and we'll have a bearing failure. Well, this had traditionally been welded using atomic hydrogen. And atomic hydrogen is a great process. It was invented over 100 years ago by Dr. Irving Lemur. I'm going to put some links below because we've done some talks about atomic hydrogen. It's an interesting process, but it simply doesn't lend itself to automation. As you can see here, you have to control not only the position of the torch, but the arc length with one finger. It's simply not a good robot process. So the obvious solution is, once again, is plasma welding. But it took us quite a while to convince people of this, because the theory was you cannot run the materials through a plasma torch that are necessary for ground engaging wear without damaging them. Because what this is 60% tungsten carbide in a chrome nickel silicon boron matrix. But before we developed this process, this is how it was done, with atomic hydrogen torch and then this material. It's called tube borium. So if you break this open, you'll see that there's tungsten carbide particles inside of it. And the sheath itself becomes the binder that holds these particles onto these ground engaging surfaces. This is how it was done for 100 years, and there's a lot of industry inertia. These are also extremely large particles on the order of 20-30 mesh. And so industry assumed that we had to have large particles in order to avoid wear. So you can see we had to change a number of paradigms. We have to change the process. We have to change the filler material, and we have to go from manual to automatic. But once again, the advantages outweighed the challenges. So it took quite a bit of proving, but there's a way to measure wear resistance called G65 or B611 testing. We did extensive testing on this material and some of the older style materials to prove that indeed this is a better process, more wear resistant. So as soon as you switch over to plasma welding, once again, you're able to run virtually any material through the torch you'd like, and you can run the hydrogen gas, which allows you to deoxidize the weld. So once we did all of this, we had to prove that the large carbide particles were simply from the past and no longer necessary. So we modified one of these plasma torches to enable us to run large carbide particles, 20-30 mesh, rather than the 100 mesh that we ended up settling on. And so sure enough, we were able to prove using the ASTM standard wear resistance testing that small particles are actually advantageous. And the particles in this tube are also agglomerated and centered. So this is standard carbide, much like you'd see on machine tool inserts. So it has a cobalt binder. We decided to upgrade the carbide, so we went with a macrocrystalline carbide that has no cobalt in it at all. So to convince industry to go from steel binder, agglomerated carbides with cobalt, to chrome nickel silicon boron with macrocrystalline carbides was quite a challenge. But in the end, we were able to prove that it worked much better, and the goal in our case was to find a process and a system that would allow us to automate the process using a robot. So all these surfaces here now are welded with a robot and plasma welding. It's worked out well. And what's interesting is as we've improved the life of both the bearing and the cutting structure on RockBits, it's pushed the failure mode to new areas. There's a small hole here on the back of a RockBit called a ball plug weld. And this ball plug used to be what you put your least skilled welders on. Anybody could make this weld. Well, after the bearings started lasting longer and the cutting structures lasting longer, this became the point of failure. And once again, you could not solve the problem manually. So here's a cross section of the ball plug weld. And the way we solve this is with the robot, because in order to make this weld, you have to move the torch so that we impinge on the bottom of this part extremely quickly, staying ahead of the weld, and no human can possibly do this. So this was, we caused the problem by making the bearings last longer, and then we solved the problem by going to a robotic ball plug welding operation to make a move that no human being could do. And at the same time, you can see that this ball plug is a dissimilar material. In order to improve the fatigue life, which was the failure mode, we switched from a mild steel welding wire to a high nickel welding wire with a much higher fatigue life. So there's a bunch of lessons we learned in working in RockBits. We had to change processes, we had to change filler materials, we had to change part design, and we had to change attitudes. But in the end, this has worked, and it's working all over the world. So My point today is on your products, whatever you're trying to do, you need to consider redesigning it, changing your processes to facilitate automation. Otherwise, you'll be stuck with your paradigm and you cannot improve upon it. Well, I hope you enjoyed this episode today, and come back again. We're going to be talking about some other lessons I've learned the hard way over the years. Until then, take care.